Hi, I'm Alexis Brower with Astra Technology. I'm here with John Hedengren. We're going to present some of our recent successes in advanced monitoring in subsea, specifically on a TLP in West Africa. So Astra Technology really began about 20 years ago. We started monitoring subsea deepwater risers and pipelines, and our most recent success has been on TLPs in West Africa. Our goals are clearly not only to protect assets in the harsh offshore environment, but also to prevent, to detect early warning signs, to prevent some of these catastrophic events from taking place. Our goal is to provide information, needed information, to prevent instead of react to some of these events. Astra Technology provides advanced instrumentation for all subsea fields, pipelines, risers. We have experience with LNG facilities and pipelines as well. Last year at OMAE in Rio, we presented a paper on Devil's Tower, which was a nearly 60-mile tieback in the Gulf of Mexico in deep water that we instrumented for pressure, temperature, strain, and we instrumented along the entirety of the pipeline. This project went online in 2008, and we've been continuously monitoring for the past 5 years, a little over 5 years now, with much success. And yeah, you can find that paper in last year's conference. Some of our other previous instrumentations were on spars and semi-submersibles. We've monitored the risers for vortex-induced vibration, and also monitoring in the touchstone for fatigue. Troika was our first subsea pipelines we monitored, I believe in 1997. And we've also monitored drilling risers. Here's an example, the Ocean Clipper, where our sensor stations are placed along the drilling riser. Just a brief overview of how our systems work. We excel in fiber optic technology and fiber optic sensing technology. So not only are our lines optical, but our sensors are as well. And this is an example of a fiber optic sensor. What we have are small gratings placed into the glass of the fiber optic, and what we're measuring is the signal, the change basically in the wavelength of the light that we send down. So some of that light, depending on the change in the gratings, is reflected back, and we're measuring that change in wavelength. Here's an example of the relationship between wavelength and strain. We're measuring the peaks, and the peak will shift to the right in tension as those gratings are spaced out further. And here is an example of compression, where the peak is shifting to the left. And then I'm going to hand the floor over to John, one of our key guys in this recent project on TLP. Let him explain that to me.
Okay, thanks Alexis. So we instrumented a TLP in the west coast of Africa. The sensor stations were placed directly on the tendons. The key thing about this is that this TLP was constructed in 2006, and just in 2013, this year we installed these. We had to make a couple innovations in order to be able to do this project. In particular, we had to have the sensor stations be diver installable. We've done ROV installations previously. This was our first experience with diver installed stations. Now, one of the things that we had to do in working with these stations, we had to make them very ruggedized. Rugged stations, you can imagine fiber optics, you think very fragile. A lot of the engineering and the development went into the ruggedization, making these so that they could be installed. We all know the upstream environment. It's a very harsh environment, and you need to have instruments or equipment that can withstand the extremes in that environment. So this is our sensor clamp that we used and designed. Before we installed this sensor, the sensor clamp, we wanted to ensure that it would be able to withstand the stresses, and so we performed a finite element analysis, and in this case we went up to 70% of failure, up to 25 KSI stress, and we had to try to design this test article so that we could get a very uniform 25 KSI around the center of this pipe. And so these are the results of this analysis. We wanted to avoid any local areas of inelastic deformation. And this shows the compression and the tension, doing this under compression and tension, both of these about a uniform 25 KSI for the forces there. Now, let me go on to we also attached some resistive strain gauges to these sensors, these test articles, and compared it with our fiber-optic sensors, and showed excellent agreement between the two. You can see very slow changes in the strain, but also very fast changes, very rapid changes, up to 70% of failure on those test articles. Now this shows the compression testing results. One of the things you'll notice at the very bottom of this plot is the temperature in the workshop that we were working in. It was a cold winter day this winter, and down in the 40s in the workshop, and then they kicked on the thermostat and heated it up. The issue with that is you need to have temperature compensation on your strain gauges so that you don't report the false sensitivity as strain instead of the temperature change. I'll show that to you later. It kind of surprised us once we installed it on the TLP. We thought that the seawater would be fairly uniform temperature right at a thermal climb. So we had a bit of a surprise later. I'll show you some of those results. Here's our 4-point bending test as well, the finite element analysis. And again, excellent agreement between the conventional strain gauges and the fiber-optic strain gauges as well. Okay, so now I'm going to get into beyond the test. Now we're going to talk a little bit about the actual installation, of these bands. And you can see the marine growth. This had been in operation from 2006. So the divers have to go in first of all and go ahead and clean off the marine growth and remove the polyethylene coating on the TLP, and then clean it with a water jet, polish it down to bare metal. Now this first picture shows the diver with the clamp swimming down to the TLP. He had about 15 minutes by the time he got the clamp to when he had to put it on, because of the adhesive material that would cure and harden, and so he had a limited amount of time to put that on. And you can see that he opened up the clamp, put it around the tendon, and then strapped it down, ensuring that the clamp was positioned in the right way for some of the bending. We had to have those sensors aligned to the north on the one particular sensor so that we could get the bending modes as well from these sensors in addition to load. Okay, so I'm going to peel back some of the layers on this clamp, and we'll look at some of the hardening that took place. We attached the fiber optic sensors to two bands that encircled the tendon, and then a polyurethane coating that went over everything. We actually had to debond the fiber optic sensor from the polyurethane to avoid some of the elastic adhesion that the polyurethane would have on the fiber optic sensor as well. So a number of innovations that took place with the design of this clamp, making sure it could be diver installable and ruggedized as well. So these are the results of our temperature and strain gauges, and this was a thing that surprised us about the temperature. We thought it would be, equatorial waters, fairly constant temperatures. It turns out we were right at, with a 60-foot sensor station, we were right at the level of a thermocline, and that we would go above or below that as the thermocline moved up or down. We had temperature compensation to take care of that. You can see that the strain from the TLP, this is the tide action that we're seeing over the course of 4 days, the 12-hour tide cycle that you see. The fuzzy band, that's the wave action that we saw. So we see the longer amplitude tides with the much shorter amplitude wave action as well. Okay, so this just shows, as I mentioned, tide and wave, and then on the right-hand side you see a plot that shows if we didn't have temperature compensation, what the load signal would look like, and it clearly is not representative of the forces of the tide and the cycle there. Okay, I'll zoom in on the wave action here. This is just the 3 to 7 second periods that we saw. We saw a number of surprising things when we installed these sensor stations. We'd go to the operators and say, well, what happened here? And then they would say, wow, we've never been able to see that before. So some of the sensitivity on the waves, we did a fast Fourier transform on the wave action and saw, typically 3 to 6 second periods for the waves. We also saw something right around 50 to 100 seconds as well. And I've asked many of you on what that could be. I've had a couple different theories on that. The natural frequency, the resonant frequency of the platform itself. MODEC actually confirmed that was probably it. I also heard from the hydrodynamics folks that it might be long waves in the ocean. And somebody else told me, it's just artificial, you should have filtered your data. So anyway, let me go on to the next one. We saw this, these sensors change, and we went to the operator and said, what happened about 10 minutes ago? He said, a boat came and docked up to our platform. So you can see 2 of the sensor stations that went down, 2 that went up, and we were able to pick up a boat docking. We also had, while we were there on platform on site, a storm, a squall come through, and we could see the impact of that on the loads as well. The one thing we're excited about seeing is we understand that whales come through that area and regularly scrape off their barnacles on the tendons of the platform, and we hope to be able to pick that up as well. So we're looking for whales for our next one. This is the tide. These are the tide cycles. I've kind of zoomed in on that. You can see the 4 tendons, and they all track very well over these 12-hour periods. We have the software set up so that it is a web-enabled platform so that you can view or monitor this data from anywhere on the corporate network. And we find that monitoring systems, it's very critical to have that element, because the data, you want to give it to people who have the ability to take action on that data and make it very accessible to the people that need it. So this is our web architecture that we use to both do the calculations and disseminate the data to the corporate network. So just in summary, these advanced monitoring systems, in Astro Technology, works on flow lines, risers, tendons, subsea structures where we need to be able to see the pressure, temperature, strain, and vibration analysis as well. We saw in this project where we installed the TLPs on the TLPs that unique and interesting events that took place, events that they hadn't been able to see before in that amount of resolution and sensitivity. We've also been able to take this system and synthesize the data into actionable action, be able to distribute it to the key decision makers. And we have future activities that we want to do as well, such as automated load balancing, particularly during drilling, and abnormal event detection as well. Be able to pick up things that preemptively so that they can take action. Let me just go on to mention one thing that we are currently starting up, which is a joint industry project in collaboration with NASA. If you're on this list, we want to talk to you, and even if you're not on the list, we want to talk to you about joining this collaboration to meet some of the great challenges that exist in subsea monitoring systems. Right now for phase 1 we have 7 specific deliverables. More information on this is available on the Astro Technology website. So thank you for your attention, and look forward to answering any questions.